Chapter 6, Part 1, Electricity. So, when it comes to the beginning aspect of electricity, the first item of business is to consider the definition of charge. And charge is the basic unit of electricity, analogous to mass for matter. Benjamin Franklin is credited with given the name positive and negative charges, and you will find that we will have two types of charges in physics. So, like charges repel one another, unlike charges attract one another. Most important understanding. An object having equal amounts of positive and negative charges are said to be electrically neutral. Now, consider the following experiment. If you have a plastic ball held by a string, is touched with a hard rubber rod, and this rod has been stroked with fur, as in shown in number 2 here. And now if you touch that rod to a plastic ball, suddenly you get a repulsion between the two, as shown in number 4. What's going on? So what has happened is, now if you have a charged rubber rod that has negative charges that's been stroked with fur, and if you have a glass rod that has been stroked with silk, and what we find is that when you stroke glass rod with silk, you effectively put positive charges on that rod. Now the two balls will attract each other. The process of rubbing rubber with fur does not create charge, but it separates negative and positive charges, which effectively transfer negative charges to the rod. And this is an illustration of that. So what is charge? Every substance is composed of tiny bits of matter called atoms, which are composed of 3 kinds of elementary particles. And elementary particles are those particles that do not have a measurable internal structure. The positively charged proton has the mass shown here, 1.672 10 to the negative 27 kilograms. The negative charge electron has a mass of 9.11 times 10 to the negative 31 kilogram. The electrically neutral neutron has the mass of 1.675 times 10 to the negative 27 kilograms. The structure of an atom consists of a central nucleus of protons and neutrons, with electrons moving about the nucleus. An atom is electrically neutral. All atoms are electrically neutral since its number of protons, positive charge, is equal to the number of its number of electrons, which are negatively charged. So here's the notion of a carbon atom. It is thought to have 6 protons, illustrated here in red. And about the nucleus outside, there are 2 electrons close into the nucleus and 4 in the outermost shell. That's the rendition of the carbon atom. The net charge, and this is an important concept, as we have conservation of momentum, conservation of energy, we also have the conservation of charge, which says that the net charge in an isolated system remains constant. And the unit of charge is the Coulomb, named after Charles Coulomb, And the basic unit of electrical charge is 1.6 10 to the negative 19 coulombs. And then now we have Coulomb's law. It looks very similar to Newton's law of gravity, but this is Coulomb's law. Coulomb's law states that the net force between two electrical charges is inversely proportional to the square of the distance between the charges and directly proportional to the product of the magnitude of the charges. That's Coulomb's law. Here is the rendition of the law. F is equal to some constant K, the product of Q1 times Q2, divided by the distance between the two charges squared. And his Coulomb is credited with having measured this value K. Therefore, he's the first person, and that's why we give this law, name it, and in honor of him. How far apart should two electrons be if the force each exert on the other is equal to the weight of the electron at sea level? And you can then formulate the weight is equal to the mass of the electron times lowercase g, and that's equal to capital K, Q1, Q2 over R squared. Solve that for R is the square root of K, E squared, M sub E times G. Put in all the numbers and can make the calculation, 5.1 meters. An electrically charged body attracts small uncharged objects such as dust particles and bits of paper. That was a pretty remarkable phenomenon when first observed. And the attractive force results from a separation of charges. Now that's the important thing. That's when the two kinds are manifested when we arrange to separate them. And that's what effectively happened previously when we stroke a rod with fur. We can separate the positive and negative charges. Here's a case then. You can comb your hair briskly, and then once you do that, because of induction, the charges on the piece of paper, you get positive charges pulled to one end on the bits of paper. Negative charges pushed to the other end. And the comb is already negatively charged. Opposite charges attract, therefore you get this attraction going on here. Here's a case in point.
An electroscope and a pair of metal spheres will be used to demonstrate electrostatic induction. If one of the spheres is charged, the sphere can cause the electroscope to deflect. Now we'll start with both spheres neutral. The spheres are placed in contact with one another. The negatively charged rod is brought near but not touching one of the spheres. The spheres are separated and the rod is removed. When one of the spheres is touched to the electroscope, the scope deflects. What will happen if we touch the other sphere to the electroscope as well?
Okay. Let me go to.
The electroscope goes back to zero. The charges induced on the two spheres are equal and opposite. This animation shows how the charges develop on the two spheres as the charged rod is brought near.
Okay. Now, Coulomb's law resembles the law of gravity as I indicated. However, gravitational forces are always attractive, whereas electrical forces may be attracted or repulsive. Gravitational force dominates on a cosmic scale. Electrical forces dominate on an atomic scale. And then we have different kinds of matter, conductors, insulators. We have semiconductors as well. And we also have diodes and transistors can be made. Diodes are semiconductor devices who only allow current to flow in one direction. And transistors are semiconductors whose conductivity can be changed as will. Notice I mentioned the word here, current. We will talk about that in a moment. Now, superconductivity refers to the loss of all electrical resistivity by certain materials at very low temperatures. We are now in great research to try to find superconductors that exist at high temperatures. Current. When current flow from one place to another, when charge flow from one place to another, we say we have an electrical current. Most practical application of electrical phenomena are based on the understanding of electrical current. And here we have then the amp. 1 amp named after Andre Maria Ampere. 1 amp is 1 Coulomb per second. And this is where we get the notion of 1 amp. And the notion of charge flow is like a water faucet already full with water, a water pipe already full. As soon as you open the nozzle, you get charges to flow. The same is true on the right here. As soon as you connect the battery to a resistor, in this case a light bulb, charges immediately flow everywhere in that circuit. And notion of potential difference, a voltage is the electrical potential energy per Coulomb of charge. Potential difference is thought of as the work a unit charge can perform as the charge travels from one place to another by an electrical force. So force times distance, of course, in order to have work done. So it's an electrical force involved, and the charge moves some distance, and we have work per unit charge. Here we have then the notion of that. Once again, the flow. A battery is a tremendous instrument, and the normal potential difference in a car battery is about 12 volts. A car battery is made of 6 cells with 2 volts each connected in series, as illustrated here. Now, ohms is a measure of the resistance of a material. It's the opposition to a flow. Previously, an example of the light bulb, the battery is the pusher of the electrical charge. You have a current, and then you have an opposition is the resistance. 1 ohm is 1 volt per amp. And here's an illustration. We tend to represent in a circuit the battery in this manner, positive and negative and positive charges at each end, and the resistor in this manner. You can connect a circuit in this manner there. So Ohm's law holds only for solid metal conductors. The resistivity of a metal wire depends on its composition, its length, its cross-sectional area, and its temperature. And here's an illustration of Ohm's law. And you can make a calculation. How long can a 12-volt car battery with 60 amp hours capacity power the lights that have a resistance of 4 ohms? I is equal to VOR, in this case becomes 3 amps. Time then is equal to 60 amp hours divided by 3 amps, give you 20 hours. Another example here. Okay, power then is current time voltage, and you can have that type example shown here as well. What is the greatest power allowed through a 15 amp circuit breaker? And so it's 15 amps times 120 volts, 1.8 kilowatts in that case. And illustrate here a method of calculation. All right. So this takes me to the end of this section. All is well. I'll see you later.